Morning, everybody. Happy New Year. I'm finally getting around to doing this little video that I've been wanting to do for a while, sort of a way to kind of give back some of the information I've gotten from the YouTube community, but in a slightly different way, a little bit less scientific. What I want to try and do is provide a little practical insight into stepper motor sizes for those of you who are looking at designing and building your own CNC machine. I've seen lots of inquiries out on the web about, what size motor should I use? And the technical 100% correct answer is, if you know all your drags, if you know everything you're going to need to know about torque and gearing and etc., you can calculate what motor you're going to know. But if you're building your CNC like I've built mine and like so many others out there have built theirs, where they've got an idea and they're going with it, you don't know that stuff in advance. So, how do you select your motor size without any practical experience? So what I want to give you is the insights I've come up with in practicality in building my machine. So let's take a look at it. What I've got in front of me are the three most common stepper motor sizes that those of us in the, I'll call it hobby, are playing with or are using. At the small end, and I had to write on the back of these so I could remember them, is a NEMA 17. Most common on real small 3-axis machines, 3D printers, etc. This middle one here is a NEMA 23, and this big mamma jamma down here is a NEMA 34. So let's talk about how you remember what the sizes mean. So I did a little studying before I sat down here and just started blathering on. And first off, NEMA, which I knew, but I'll share with you, is the National Electrical Manufacturers Association. These guys have a standard for flipping everything. There's got to be a racket in there someplace. I want to come up with my own standard and let people pay me for it. But anyways, they're the ones that set out the standards for these motor sizes. And most of what it relates to is the frame size or the bolt layout, the shaft diameter. But what it doesn't talk about is length, and I'll get into that in a minute. So anyways, a NEMA 17, this is originally a US-based standard. And so these numbers actually have a meaning in English measurement. A NEMA 17 is approximately 1.7 inches. 23 is 2.3 inches, 34 is 3.4 inches. So it got a whole lot easier for me to start remembering these numbers once I knew what that meant. It also means that these hole sizes you can work with real easily. Like the hole sizes in a 23 will take a number 10 machine screw real well. 34 will take a 1/4 inch machine screw real well. And if you're out there on eBay and you're shopping for these things because you're sort of designing one out at your desk, and you see all these numbers are all in metric measurements, the shaft diameter, the spacing of the holes and everything. If you convert all those to English, they convert very nicely. But anyway, so that's what they mean. That's what their size numbers mean. And then they come in different torque ranges. That's the next major thing. These three I've got right here. This one here is 57 ounce-inches of torque. So 1 inch out, it will hold 57 ounces of weight. Not bad for this little guy. This NEMA 23, and I had to go back and take some notes, this one is 425 ounces. And this 34 is 1,232 ounces. And I've got them all sitting here side by side so you can sort of get a feel for what they look like side by side. If you've seen a 3D printer, that's what these are. Or this general size. This size is used in a lot of smaller CNCs. And then these big ones here, especially if you're gearing them down, you can convert a full-size vertical mill with something this size. So let's talk about length a minute. The standard that they are related to, this NEMA standard, talks about shaft diameter and screw spacing and physical dimensions, but not length. And what I have learned is, and here's one that first caught my attention. This is a NEMA 23, 425 ounces. If this was a smaller motor in torque specification, then it would be shorter. And I'm sure someone really smart out there knows why, but the more torque they have, and I assume it has to do with the magnetic force, more torque they have, the longer they are. So if you had like a 250 ounce NEMA 23, it might only be about half this long, but all the face dimensions would be the same. So a note here is, if you build to a NEMA 23, if your machine is built and has motor mounts for NEMA 23s, and you buy a 200 ounce motor and you find, that wasn't enough, the same frame and shaft diameter, and you can get a bigger motor as long as you have length. So something to consider if you're on the fence. So let's talk a minute about what I selected to use for my machine. I went with this bad boy. I'll get out a scale and I'll put it in the notes. That thing is an easy 5 or 6 pounds. That's a heavy motor. I went with this one. This is a 34 at 1232 ounce inches. It's an 80 volt motor. Runs at 7.8 amps. And I'm kind of the mindset that go big or go home. And so I went with the bigger one. Again, I'd seen these little jobs. I'd never seen one of these in person, and I really didn't have a concept of what 425 ounce inches was. I'd never seen these, and well, it's big. An example of how big it is, I bought a 20 millimeter set of ball screws and linear rails that came with zero backlash couplers. Yeah, they fit this motor. And I had to buy a whole different set to fit this shaft diameter. So somebody's expectation was I wasn't using a motor this big. And those were 50-inch rails and screws. The machine I'm building is 4 foot by 4 foot, gantry style with a fixed table. It's got round linear rails. I did a review of the linear rails. It's one of my other videos. But I, again, didn't know. I decided to go with this frame size, and I went with the 1200 ounce inch ones because they were cheaper than the 800 ounce inch version. So that was a no-brainer to me. The expectation is if this is 1200 and 800 would have been about so long. So it would have been just a little shorter, same frame size. So, but these were cheaper, so hey, what the heck? I bought them as a set: motors, steppers, and drivers, or steppers and power supplies. And each one of them has their own power supply, as opposed to some of these down here where you just run one power supply, runs multiple motors. This is just a little 12-foot job. So this is the one I went with. They're monsters. I have a gantry machine, or a gantry style machine. So I'm running 2 of these on the y-axis, and I've got the dip switches on my stepper drivers set to half amperage, so they're only running at half their output. I'm probably going to wind up running that back up to full power, simply because my z-axis is so freaking heavy that I would have to have my ramp up and ramp down speed so slow that it would be less than optimal. So anyways, this motor here, I decided that I didn't need a big monster like this for my z-axis. I mean, really, how hard could it be to raise the z-axis up and down? It's going to have a spindle or a plasma cutter tip on it, one or the other. You know, how tough can it be? So I ordered this one later. That's how come this one isn't on my machine right now. I ordered this one later. Now that I know how heavy my z-axis is, I question whether this is enough motor. I'm running these direct drive, direct to the ball screw, trying to minimize lash as best I can, reducing the only potential for lash is actually in the ball now. If I was going smaller, definitely in the 2-foot range, I would be looking at 23s. These are just way too freaking big. You don't need anything this monstrous. I do like these on my big 4-footer. I guess it's, as much as a comfort thing, I don't have to worry about having enough horsepower. So hopefully this is giving you a little bit of an idea. These are good for little tiny machines, little desktop size machines. I have a full set of these with little stepper drivers that I'm going to build out kind of really just a little desktop job just for fun, for trying things out. And then I'm going to step scale it down to match my big machine. So I can be playing with how my big one will operate on a desk size version as far as travel and movements goes. So that's what I have these for. This one here, again, my Z axis. This one here is my X and my Y's. That's a big motor. So I hope that gives you some idea of what these things all look like side by side. This one's wired up here for my Z. It's going on later this morning. If you guys have any questions, if you folks have any questions, go ahead and put it in the comments, and I'll do my best to answer you. This was not meant to be scientific, just a practical discussion of stepper motor sizes. One other thing I learned, and we'll end this on a trivial note, they make stepper motors, and these aren't the most common, but they make stepper motors where the body is round. If you have an opportunity to get those at the right price, round ones typically have more torque than a comparable size square one. So keep that in mind. All right, folks, you have a good day and have a good 2016.